Ah yes, Back to the Future, the original Rick and Morty. Welcome to CS302 Fall 2022 Assignment 8. And for this assignment, well, the theme is going to be Back to the Future, as you can see right there. And we're going to have this electric DeLorean, which of course, if you've seen the movie Back to the Future, you definitely should at some point watch it. It was a fantastic movie series. So in that movie, they had this DeLorean time machine car. And if it goes up to 88 miles per hour, it's able to go through time using the flux capacitor. So, of course, this paragraph right here is just me just goofing off, sort of trying to emulate a Doc and Marty dialogue, which if you've seen the movie, you can tell which person is talking out which sentence in that description. But in this assignment, we're going to assume that our DeLorean is not gas powered. We're in the future now. Everything is all EV. So at this point, we're going to have electric DeLorean, and we have to, of course, navigate through various power stations. So imagine you're trying to drive your Tesla from Las Vegas to LA to Disneyland. You have to go through various stops and charge your car up. So the same idea here. We're going to try to, take different paths to different stations to charge up the DeLorean. And once the DeLorean hits 62.5 kilowatt hours, it has enough power to hit 88 miles per hour and power the flux capacitor to go back in time and to do whatever crazy adventure that Doc and Marty have to do. So of course, as you can see, we're going to have a graph problem where each edge will be a road or path. Now each road does actually use up some of the battery power to take that road. But then of course, once you reach that station, you of course power up the DeLorean with however much power that station can provide. And of course, at some point, once you hit that amount, 62.5 kilowatt hours, you're good. And of course, the car cannot have more, well, I guess for this car, I'm going to say, it cannot have more than 75.5 kilowatt hours. But I will go over that more in the actual details of the assignments. Let's go ahead and now discuss data structures needed to implement this graph assignment. Okay, so for this program, you're going to have to store the graph into some kind of an adjacency list. So since each edge is going to be a weighted edge, you have to store the weight of each edge and also the destination of the edge. So in this edge struct, you have this string station, you have this double distance. So string station is going to really be that point B, or when you're going to a node. So this edge goes to the node, and the station is going to be a name of that node that the edge goes to. And the distance will be that weight of this edge. Okay, so now we're going to have to use this map data structure as our adjacency list. Now remember, for the examples we covered in class, what we did was we used we used nodes as integers, or the integers were the names of the nodes. But since you're going to be using strings as their names, we're going to have to use a map data structure. So think of it as really the same idea, except that the map is going to be your array, because the bracket operator can be used to look up some entry by a string. So we're going to have this map. It maps a string, which maps a node to a list of its edges. So let's say you have a station name, and it maps to all the neighbors of that node. And of course, you're going to have a set of these. And I'll sort of give you an idea right here. So now, of course, you can name your variables. I named a map of charging stations, which was a rather large variable name. But of course, you can update that. You can use a smaller variable name if you like. So anyway, suppose if we have, let's say, we want to store the following edge where we have a sort of a point A. Let's say one of our nodes is literally called point A, let's say, and of course our sort of the edge that goes from point A to point B, that's going to be an edge with a distance of 1.7. We store this into the graph in the following way. So we have our map of charging stations, and then point A, we want to look up point A's neighbors list, and of course push back this edge that contains point B, 1.7. Now, of course, you're going to have to overload a constructor for the edge struct in order for this to work. So this is going to be the idea. So whenever you use map of stations and you have a variable, or sorry, a string node name, that returns a list object. And of course, you can do a pushback, and of course you can traverse it as well. So here's a way if you want to traverse all the neighbors. So we will be doing a DFS type traversal for this assignment. This method is going to, a little typo right here, I can fix that later on. But anyway, we have this this for loop right here. We have this iterator neighbor and a map of charging stations. It should have been stations, but you know, not a big issue. I'll fix on the PDF. And then point A dot begin. So it's going to return the iterator of that first edge, or first neighbor of point A. Then of course neighbor not equal to map of stations, and it should have been actually point A right here as well, not point B. But of course, again, not a big issue. I'll have that fixed before I post this video up onto YouTube. .n and neighbor plus plus, and of course you're able to traverse each neighbor, each element of that neighbor's list, and of course you do dereferencing dot station, dereference neighbor dot distance. Now of course you can use the following. So this is one way. This is the first loop you can use to traverse to all the neighbors. So of course when you're calling DFS, you have to call DFS on each neighbor, as you remember when we went over this in class. But here's the other method, a much more condensed method, which I really would think that this would have to be more preferred, because it's a very nice and compact version. So this is the same idea. We had this for this iterator type object, I guess, iterates through all of the elements in map of stations, point A. Then of course neighbor dot station will be the actual sort of the edge, or that tells you that this edge leads to this station. Of course neighbor dot distance tells you the actual length of that edge. So really, this neighbor auto type right here is really an edge, and of course an edge has a destination dot station and a distance dot distance. So pretty much as you sort of I will give you a file, which I'll go over that file in a little bit. You're going to have to one by one insert elements into your map using the following technique, like right here. Of course you will use this for loop to iterate through all your neighbors when you're doing your DFS type traversal of your graph. So let's go ahead and now discuss the other data structure you will probably have to use. So here's our other map, which will be called charging station, and it's going to map a string to a double. So as mentioned earlier, each charging station has an amount you can charge the DeLorean's car battery up to. So for example, let's say if this station called XYZ can charge the battery 5.7 kilowatt hours, which I think that is the correct units for the amount of battery energy or power. I don't own an EV, so I'm not really super acquainted with this, but I believe that's the right units. If I'm wrong, then I guess you can correct me if I'm wrong on that. So this is going to pretty much insert, so XYZ, this station can charge the car up to 5.7 kilowatt hours. Of course, you can use this method as well to insert this, but you're going to be using this because when you arrive at a station with the DeLorean, you want to charge up the car as much as possible. So let's say if the DeLorean happens to land on station XYZ, it will add 5.7 kilowatt hours of extra energy or power into the battery. That's what this is actually used for. Now, of course, you're going to have to use other data structures as well, but here's the two main data structures you're going to have to use to just store all the data for your graph and be able to sort of use the graph and traverse it and recharge the car and so forth. Okay, so now let's go ahead and discuss the actual DFS implementation you'll have to write to implement this algorithm that's going to compute the path that gives you sort of enough power to go 88 miles per hour. Let's go ahead and discuss that next. Okay, so you're going to have to implement this DFS type function, which I call it 88 miles per hour. It's a pretty relatively creative name, given the fact it's going to be a Back to the Future themed assignment. So this function, what it does is it's going to output a path from a start node until it finally reaches a situation where the car battery does have 62.5 kilowatt hours. So the idea is that when you traverse this graph, whenever you take an edge, it's going to drain the battery a little bit. So if you look at this, this sentence right there, if you take an edge, so that distance of that edge, multiply it by by 0.346, you're going to subtract that amount away from the current car's sort of battery power. But of course, if you take an edge, if you go to the station, at the station, you can, of course, charge up the car. That's sort of the idea for this assignment. Of course, at some point, you will hit a node. When you do charge up, you will end up exceeding 62.5 kilowatt hours. And of course, that means at that point, you successfully have a path. Of course, you want to then construct the path. So the path gets constructed in a reverse order. So this function has to return a stack object. And the idea is that as you, the very first instance where you do have a situation where you do have enough kilowatt hours of battery in the car, you push that node name onto the stack, return back to the previous function. Of course, you push that station name onto the stack, and so on and so forth. That's going to construct that path in reverse order. So then, of course, if at each recursive function call, the stack returns at some point, let's say it returns a null, that means that edge you took at a certain node did not reach, it did not really get to a situation where the car was able to get 62.5 kilowatt hours of power. So that's going to be really the idea for this. So of course, you can think of how you would actually write the code for this, but of course, you have to pass in several parameters into this function where you cannot have a global variable, and you cannot pass any parameter into the function that sort of stores any path at all. So you can't pass in a predecessor array. You're not allowed to do any of that. All you can really do is just pass in the current node you're on, and of course, agency list and so forth. But you don't want to pass in anything that tells you what path you're on. This return stack is going to really kind of compute the final path when sort of a path is found that does lead to 62.5 kilowatt hours. Now, the catch is also that you may have to revisit a node at a certain point, because maybe you found one path to a node, but then you find another path that leads to a node, to that same node, but with this path, you actually have more kilowatt hours in the battery of the car. So you have to expand again as you traverse this graph. So I'm going to go ahead now and just sort of draw an example picture so you can see exactly what I mean by this. Let's go ahead and discuss this part next, and of course, then I'll go over the final remarks of the assignment. Before I go into the visual sort of description, or more of an interactive example of this assignment, I want to first give you the input files you have to work with. So this is going to be these 88.txt, which is going to just be your graph. So this really tells you, each line tells you an edge in this graph. So from station S to station C, distance is 30.5. From station S to A, it's going to be 26.2, and so forth. So the idea here is you have to read in these three contents. And of course, remember, for this case, you would read in station S, so you'd have that map of charging stations at index S dot pushback. And of course, you have to insert these two into an edge struct and then push that back and so forth. Now for the station info 1 file I give you for each station the amount you can charge a battery at this station. So at station C, you can charge it to 10.6 kilowatt hours you can charge into this car. At station A, you can charge up to 25.5 kilowatt hours and so forth. So that's the input files you're going to be working with. And then of course, using these, you have to, construct that path, and of course add, when you arrive at a node, you have to update the car's battery power / energy when you arrive at a station, and so forth. So, okay, so now I got that out of the way. Now let's go ahead and talk about the actual example, and I'll sort of give you a little bit of example trace how to see how this all works. Okay, let's go ahead and consider this graph right here. And of course, once you prompt user for the input file that contains like your map or the graph edge data, And of course, you prompt the user for the stations, or the amount of energy each station can power the battery. You then, of course, prompt the user for a starting node, which we're going to always just have S as our starting node. And of course, you also pass in an initial battery amount. So in this example right here, we're going to have S as our starting node, and our starting power in our battery will be 2.0. So what we're going to do is, starting from S, so we're going to use DFS type traversal. And I'm going to actually, let's say we're at S, we have neighbors B and A. Let's suppose I happen to choose B first, just because. Let's see what happens if I choose this neighbor first. So I'm going to go ahead and pick this edge right here that goes to node B. And we have to first compute the amount of energy we're going to lose when we do make this trip from S to B. So in our car, we have 2 kilowatt hours. Subtracted by 4 multiplied by 0.346. That's going to give us the value of 0.616. So we're going to store into some kind of a map that tells us when we arrived at node B, we arrived with 0.616 kilowatt hours. So from B, I want to go ahead and try a neighbor. So of course we have to charge up our car by 1 kilowatt hour, because at node B we see that number 1 above it, which means at node B or station B we can add 1 kilowatt hour to our battery. So let's go ahead and try the node from B. Let's try a neighbor D next. Okay, so we're going to have 1.616 subtracted by 10 multiplied by 0.346. And that will give us a negative number, which means that we can't even make that trip from B to D. So that edge is discarded. Okay, let's try our other neighbor from B. So B has neighbor, it goes to C. Okay, so again, we're going to have 1.616 subtracted by 7 multiplied by 0.346. And we get a negative result that way as well, which means that from B, with the amount of battery charge we have, we can't make it to either C or D. So we have to go back to node A. So we're going to go ahead and hit the reset button, go back to S. Oh, sorry, not back to A. I'm sorry. So from B, we go back to S because we started from the node S originally. And we sort of return an empty stack back to S that tells node S that, okay, the neighbor B led to a failure. Okay, let's go ahead and now try neighbor A from S. So we're going to reset. So now we're back to just, our 2 kilowatt hours in the car. We're going to take that trip from S to A, which will take us, let's take a look. So we have 2 subtracted by 3 multiplied by 0.346. So when we arrive at node A, we're going to have the value 0.962. That's the amount of power we have when we arrive at node A. Of course, we can add 2 to this because we can charge up our car by 2 kilowatt hours. And of course, I'm going to now, from A, I have to pick a neighbor. The only neighbor we have is B. So I'm going to now try to go to node B. So we have this amount, so 2.962, subtracted by 2, multiplied by 0.346. So from A, we actually found a better sort of path, a path that gave us actually this much power. 2.27. So we're going to go back to B again. So with a traditional DFS, since you already seen B earlier, we're not going to go there again. But we do actually, in this case, we should go back to B if we found a different path that got us to node B with more power. So the previous, the last time we got to B, so the one way we got here earlier, it led us with 0.616, but I found another path that gave us a better more amount of power at node B. So I'm going to overwrite in my map that sort of stores the powers when I arrive at the station. Now, let's say, for example, from A to B, let's say if I wasn't able to get a better amount of battery power, then I would not have tried B. But I tried B in this case because I found a better path. So I'm going to stop talking about that. Okay, so now from B, let's say once again I choose neighbor D. Again, I'm going to do the same thing again because now we found a better way to get to B. Okay, so now from B, I have 2.2, so 2.27 plus 1 to get 3.27. I'm still not quite there because I need 3.5 units. I need to be complete. So I have 3.27, it's not quite there. Let's try the neighbor. It goes from B to D. So it's subtracted by 10, multiply it by 0.346. And that gives actually a negative value. So from B to D, we can't make this journey. We don't have enough power to get to node D. So you have to discard this edge. Now for B, we have one more neighbor that goes to C. So what we're going to do now is, again, we're going to try 3.27 subtracted by 7 times 0.346. And that gives us actually, we arrive at the station C with 0.848. But if I do arrive at this station, I can, of course, add 3 kilowatt hours to my battery amount, which will give me a total of 3.848. So I met that threshold of 3.5. So in this path right here, from S to A to B, and then B to C, this path sort of gave me, if I follow this path, I will end up getting 3.848, which will be enough power, well, my target power I need. So there we are. So of course, you traverse your graph in DFS type fashion, and once you have that moment where you do have your threshold met, you have to start pushing stuff onto your stack. You push kind of node by nodes. As you return back to previous functions, you have to push the node or station name onto the stack and so forth. So in each function call, when you call this DFS function, you return a stack, and of course if it's empty or it's not empty is the question really. And of course if it's not empty, you have to do some work. If it's empty, that means that path led to a failed search. You have to, of course, try a different neighbor for that node. Okay, so now let's go ahead and just do a quick remark. I'll maybe just do a quick sort of demonstration of the program, and then that would be it for this video. Okay, so before I run this demonstration, for this program, as you already have probably could guess, it's going to be all STL is allowed. So of course, stack, unordered map, list, it's all usable. So you don't have to worry about having separate header files. Everything can be in one main. Of course, use all the STL as you would like. Now, of course, the rules you have to implement a DFS type traversal. So you're probably guessing that you might be able to actually just do Dijkstra's algorithm on this assignment. You probably could, but just use DFS because we're trying to learn DFS actually at the moment. So to compile this program, of course, I would just g++ main.cpp. Okay. So I have these two input files, and of course, this is going to be the input I'm going to be using on CodeGrade as well. So I'm going to run this. And the charging station map, I believe I call this 88.txt. And then enter charging station info file. So it's going to be station info_1.txt. Then enter the starting location. So it's going to be station, station S. And I believe I used 13.6 as my initial battery power. And of course, this is the path that we can use that's going to lead us to get 62.5 kilowatt hours. And of course, Doc has to give a message to Marty. We have to go back in time and sort of help Marty McFly's kids, because one of them got into trouble, I think, with Biff's grandson, I think in 2015. So that's going to be the first input case. And a second one, of course, is going to be a failed case. So it's going to be, I think I called it Great Scott, another sort of favorite line by Doc from Back to the Future. And the station is going to be, it's going to be station info2.txt. And of course, we start from station S again. And it'll be again 13.6. And then this graph, there is no way to get, there is no such path that will give us 62.5 kilowatt hours. And of course, Doc has to give us this message right there. So that's really about it. And of course, these two inputs will be actually tested. I'm going to probably put this into the PDF as well. And on CodeGrade, we're going to test these 2 input cases, and that's it. So I hope this video did give you an idea of how to work this program out. So of course now just happy coding, as always, stay safe, and till next time.